Hello, it's Mike. So, this is the second video of the series on the actuarial modeling, and today I'm going to use Mathematica to solve even more problems. Now, before we start, today we'll talk about maximum likelihood estimator, a rather tedious computation. Now, before we start, I'd like to look at some of the basic computations. You can generally just have your laptop open and use Mathematica as a complex calculator. For example, above you see this is a very typical array of numbers, or list if you prefer that terminology better, and you can calculate skewness, and you can use a lot of built-in functions such as n integrate. And you see above n integrate we have very basic calculation, but you can just add more complexity to it, and just shift enter and it'll give you arithmetic immediately. And there's built-in functions such as PDF, the density function of probability distributions, common ones like from discrete Poisson distribution to continuous Pareto, gamma, etc. So for n integrate, for example, a really simple example would be integrate from x from 0 to 1, and you probably know already is a third. And here, actually, backfired sometimes. Okay, a third. Alright, so n integrate will usually give the numerical answer, and integrate will give you a precise answer when that is possible. So we have the skewness, and unsolved can also be used to solve complex equation systems, such as this is really a two-variable system. Okay, now back in business, maximum likelihood estimator. So usually you start with finding the likelihood function. Now here we have an example where we're observing light bulbs, and at time 4 we have 5 working light bulbs. They're still on, and they're observed for p more hours. In fact, we're going to calculate the number of p. So we're giving the following information. So one light bulb is burned at time 5, 9, and 13 each. Okay, so the other 2 remaining light bulbs, they survived this p hours of observing window. We know that the failure time is uniform distributed between 0 and omega, and the maximum likelihood estimate for omega is 29. And knowing these, calculate p. This is not as straightforward, because normally we will be able to, the question normally that will be asked is to use the MLE method to estimate the estimator. Now we're doing the reverse. We're given the MLE estimator, which is omega equals to 29. We're going to calculate p instead. So we start by writing out, in fact, is this portion. This would be the MLE. It's not too hard to figure out using conditional probability. These 5 light bulbs, 3 of them already, actually all of them already survived 4 hours. So the 3 of those, for those who burned, the density is uniform, 1 over omega minus 4. 3 light bulbs burnt during the duration of your observation, so to the power of 3. The rest of the 2, this is really 1 minus p over omega minus 4. Being the duration divided by the time window, which is omega minus 4, and to the power of 2. So if you take this, and I actually faithfully copied here, and you take the log of it, the natural log in Mathematica 8 is the log function, and you take the partial derivative, here d for derivative, with respect to w, well, and using another command for simplify to simplify the arithmetic expression. Now without for simplify you'll get a mass, and that's probably too much to handle, and you want for simplify to boil it down a little, and you substitute 29 into this and set it to 0. In fact, should back out the p, and that will give you p around 6.875. Therefore, choice A is the best answer. But again, the most important thing here is not the answer itself, but rather the method here, MLE. You can really use Mathematica as a very powerful tool, because once you have the likelihood function, even if it's symbolically, you can simply first take the logarithm, the natural log, and then the partial derivative, and use the built-in utility to fully simplify the expression. So the kind of work on your part as an actuary is really limited. It's simply finding the likelihood function, and then you'll be able to estimate the parameters on the fly. Hope you'll find this method to be very productive in your daily work. Thank you.